CNNs. I hope you may be taking some other course either this semester or next semester where you will get the full introduction to CNNs. We don't need to really understand what are the mathematical details of each layer. What we are more interested in is what are the architectural characteristics. Essentially, what are the characteristics of inference and training phases. So these are the CNN layers. So we have convolution layers. Here we have input feature map. It is also called input activation. And we multiply weights with input activations. And with this, we get the output activations or output feature maps. Okay. So the dimensions of weight is m into n into k into k. So here each kernel, each weight filter is k into k, and we have m into n of such kernels. Similarly, we have so many input features. So the dimensions are mentioned here. Where s is the stride. Usually it is 1. And by doing the convolution, we get an output feature map of this dimension. So input to convolution layers are n feature maps. Every feature map is controlled by a shifting window with a k into k kernel, which produces 1 pixel in 1 output feature map. Shifting window has a stride of s, which is smaller than k. And this m output feature maps, so here we generated m output feature maps. These are the m output feature maps. The dimension of each is r into c. So the m output feature maps become the input feature map for the next convolution layer. And this is the 6-level nested loop. In some papers, you will see 7-level nested loops. Okay, so that is, that's why I don't go into too much of detail of this. This will take a lot of mathematical visualization. Here we have 6 levels of nested loop for you could also see like 7 levels. This innermost levels, k into k, that is just one filter kernel. So one thing which is more important for us is there are many levels of nested loops, and that's why there are several loop optimizations that can be applied. So especially if you are from compiler background, you know there are many loop optimizations. For us, we will apply 1 or 2 loop optimizations such as cache blocking and so on. I will discuss this in the next presentation. So now there are pooling layers which realize spatial invariance by subsampling adjacent pixels. So that means, see, just as for example, my eye right now I'm seeing this block at the center of the screen. If this block were to shift to the right side, I can still detect it. Okay, so that means pooling layer, what they do is they realize spatial invariance. That means it doesn't matter whether the object is here or here or here. As long as the object is within my view, I can still detect it. So that's what these pooling layers do. And they also reduce the dimensionality. For example, here we have a 2 into 2 filter, which is a stride of 2. So 2 into 2 filter, first I apply here, I find out the maximum value. So that's called maximum pooling. This is the maximum value here, this is the maximum value here, this is the maximum value here, this is the maximum value here. So 2 into 2 pooling with a stride of 2. So stride of 2, why? Because originally my filter was here, 2 into 2 filter was here. Then it shifted to 2 here. It shifted right side 2. Okay. Now in the average pooling, we compute the average of these values. Okay, we compute the average of these values. So that is the average here. Usually max pooling I've seen more common, but average pooling is also widely used. Now, there are many activation functions such as sigmoid, tanh, ReLU. Nowadays, ReLU is more popular, especially in convolution neural networks. So in RNNs, recurrent neural networks, you see sigmoid and tanh more commonly. But in vision, that means in computer vision, you see ReLU more commonly. Okay, so now let us try to understand what a deep neural network does. So deep neural network has many layers. Okay, so each layer is giving you every further layer is giving you higher abstraction of the reality. In the initial layer, we are just seeing input pixels. We don't know what is the object. We don't have object level understanding. Then in the next layer, we find out the edges. So for example, we just now saw the Sobel edge prediction. So that is just one example. Of course, in deep learning, we are not doing Sobel edge prediction, but the next layer tries to just find out what are the boundaries or edges. Then the layer after that tries to find out corners and contours. Then from this, probably one layer or maybe 2 or 3 more layers, or some more layers deeper, we begin to identify these are the object parts. This is the hand, this is the face, this is the tail, this is the tire. Okay, and finally, from this object part, that means if we have hand, if we have 2 hands and 2 legs, that means it must be a human. If we have 4 legs, it is a animal. If we have 4 tires or 3 tires, 2 tires, it is a car. So by accumulating different objects, we come to the understanding of the whole object, or a whole person, or an object. Or let us see an example of how we read a book. So first of all, I just see pixels. Then I connect the pixels. I make the pixels, and then I see, okay, this is one character, this is the next character. This character is not same as this character. These 2 characters are separate. Then I recognize each character individually. That, okay, this is A, this is B, this is C. Then with characters, then I make the word boundary. Okay, this is one word. This is, for example, participation. Next word is recycling. I separate them. Then I separate the sentences. Okay, slowly I read the sentences. Then with the sentences, I make paragraph. And with paragraph, I make the chapter. And with chapter, I make a book. And then with a book, I make a course. So as you can see, all of these are higher level of abstraction. But I begin with a very low level, beginning with recognition of a pixel. I go all the way up to recognition of the whole meaning. Okay, that's a higher level comprehension. So that's what deep neural networks they do. Beginning with a very, very basic or low level understanding, they go up to understanding of the whole object identity.
Excuse me, sir.
Yes, please.
Sir, in this last image, as the input, we got the whole picture. Like we provided the whole picture, right? And at the end, we were able to differentiate between the different objects in the picture. So, still we had like a normal input. Then why did our picture get blurred? Like we provided a normal picture, right? And we were able to identify.
Yes. So what is your question? We provided normal picture, okay?
And at the end of the picture, we identified different objects, but still, like, why my picture got blurred? Like,
no. This picture did not blur because of us. It's just that I have scaled the figure too much. We have not blurred it. It's just that this figure was originally very small. If I taken a proper image, we have not blurred the image at all. Here, it's not that example of blurring.
Okay, sir.
This is just that we have taken the figure from somewhere where probably the picture quality was good, but while copying or whatever, maybe because of scaling, the picture looks bad. But this example is not to show you how the figure image is becoming blurred. Don't take that lesson. Okay. Now let us see the architectural characteristics of CNN layers. So these are the layers in AlexNet, one of the first most popular neural network. Okay. So we have here convolution layer and next 2 layers. Usually we have linear layer, non-linear layer, linear layer, non-linear layers. They are one after another. So convolution layer, and then we also have actually value layer, which is not shown here, for activation function. Okay. So initially we have an input image size of 227 cross 227, and then we have 3 what we call channels: red, green, and blue. Okay. And then this is the kernel size, this is the output feature map size, and this is the sprite. And okay, here the activation function is shown on the right side. That means after this set of layer, you will have an activation function. Okay. So remember, AlexNet has 5 convolution layer: 1, 2, 3, 4, 5, and it has 3 FC layers. Okay, it has 3 FC layers. Okay. So these are the dimensions you don't have to remember, just showing. So now let us see in computer architecture, we are more concerned about computation and memory. How much computations we have to do, how much memory we need to access. So number one observation is that most of the computations of a neural network, they happen in the convolution layers. Okay, most of the computations happen in convolution layers, and most of the weights are there in the FC layers. FC layers have most of the weights. So as I will show here, so around 93% of the operations, they happen in the convolution layers. And more than 95% of the weights are in FC layers. So the whole point is convolution layers have very few weights because the same window just slides over the whole image. Okay. So here, for example, the kernel size is small, and the same kernel rotates over the whole. This is called sliding window convolution. So the whole this kernel rotates over the whole image. That's why you have very few number of weights. Whereas in FC layers, you have fully connected. So all the neurons in the previous layer, they are connected with all the layers in the next layer. All the neurons in the previous layer, they're connected with all the neurons in the next layer. So that's why you have full connection. And that's why because you have full connection, each connection will have some weight. That's why you have huge number of weights. So now what our observation is, most of the operations, they happen in the convolution layers. That's why they're compute intensive. That means whenever you are doing convolution layers, you need a hardware or you need a platform which can provide you a lot of computation power. And that's why, for example, we use GPUs. GPUs have massive computation capability. Most of the weights are in FC layers. Okay, most of the weights are in FC layers. So you need to fetch all those weights from memory. That's why you need a lot of memory bandwidth. So these are memory bandwidth intensive. FC layers are bandwidth intensive. So this is a very, very crucial or foundational, observation before we design any XLA data. First of all, you have to understand which layer needs what. For convolution, if you try to do a lot of bandwidth, you don't need that. It will not benefit. Its performance will not improve. Whereas for FC layers, even if you have a lot of computation hardware, but you are just waiting for the weights to arrive. Okay, so that's why they are bandwidth intensive. They need more memory capacity and especially more memory bandwidth. Now, pooling and nonlinear layers, they do not require large amount of computing resources. So actually, for pooling layers, there is no trainable weight, right? For pooling, as you can see, pooling layer itself does not have any weights. We are just doing, we are reducing the number of total pixels. There are no new weights which are there. Pooling layer does not have any weights. And similarly, nonlinear layer, like for example, this ReLU is called a nonlinear layer. Okay, so here also there are no weights. We just multiply the previous output with certain value to get the new output. They don't need any computing resources. Okay, so now let us see the data reuse characteristics. So this is this point clear to everyone? Of course,
I have doubt.
Just 1 minute. So all the nonlinear layers, they don't need computing resources, but they have other requirements which will be clear soon. So in nonlinear layer, we are not doing a lot of computations. All we are doing is we are passing it to, for example, either TimeEdge or ReLU or sigmoid. So those computations may be there, but the other than that, it is very straightforward. Yes, please.
Sir, in the neural network first slide, sir. First slide. Can you go back? More back. Yes, here. So what are M and KK?
Yeah, I will not be able to explain it actually. You will have to read it yourself. This is not very relevant for us.
And sir, on the last slide that you showed. Yeah, here. Back.
Yes.
Back. One more back. Yes, sir. Sir, here after each layer, convolution layer, activation function is applied. What is the role of applying this after each layer?
So actually, see, if you have two linear layers, one after another, actually you can merge them in a single linear layer. So usually we have linear layer and then non-linear layer, then linear layer, then non-linear layer. We generally never have two consecutive linear layers because you can anyway merge them. Okay. Now again, there will be more deeper philosophy of how we design neural network. That is probably outside this course. There are actually, like if you go into the deep learning field, they have very, very deep explanation of how does our brain generalizes and representational power and so many terms. So probably they will give you a more convincing answer, a more deeper answer. But I've given a very simple answer that usually we never have two linear layers one after another because you can anyway merge them in a single layer. So and activation functions are they're doing a very useful. They are actually suppressing unnecessary firing of the neurons. Okay, they are suppressing unnecessary firing of the neurons. So that's why you have activation functions. For example, if you see like value, it just completely makes the negative values to be 0. Now you can say it's a lot of loss of information, but actually ReLU gives you much better accuracy than sigmoid or tanh. ReLU is used in AlexNet, for example, and ReLU gives you better accuracy than sigmoid and tanh. And ReLU is also faster for training. That means if you train a network using ReLU, you get much better training speed. So this initial very quick introduction is not sufficient to answer all those deeper questions. This is to just introduce you some simple things. Okay, is that clear?
Okay.
Sir, I have a question.
Yes, please.
Sir, like there are no kernel functions in fully connected layers. Like it directly converts into featured maps.
Yeah, because see, there is no convolution layer. There is no convolution filter which is revolving. So in the FC layer, it is just that first you have this many neurons in this layer, this many neurons in this layer. All of them are connected with each other. That's all.
Okay, sir.
Right, all of them are connected with each other. So that's what. And each connection means it will have some synaptic weight.
So it's a direct.
Yeah. So all of them are connected with each other. So that's why you don't have a kernel as such. Okay. So, okay. Okay. Now let us see the data reuse characteristics. So in convolution layer, as you can see, we have the same filter revolving over the entire image. So that's why convolution layers have high amount of data reuse. Okay, convolution, because see, first of all, actually there are many types of data reuse. For example, here this one kernel will be see here if you come here, that will be more easier. For example, you see this weights. So we have this one for example one kernel filter, right? So this is shifting window with a k cross k kernel. So let us call it one kernel. So this first kernel will be multiplied, will revolve on the entire input feature map. Then second kernel will come. That will be multiplied with the whole of image. So now you can see the same input feature map. We multiplied with first kernel, second kernel, third kernel, fourth kernel, and so on. So that's why there's a lot of reuse of input feature maps. Similarly, one kernel goes over the entire image. That means over the entire input feature maps. So now you have the reuse of the input kernel, right? Weight kernel. Right? This same weight kernel will be multiplied with the whole of the image. So that means there is a lot of reuse of this weight kernel. Okay. And input feature map, of course, that means the same input feature map, all of this input feature map, they will be multiplied with all the weights, right? So that means you have reuse of the input also. So in this way, convolution layer has a lot of reuse. Now, nonlinear layers, they don't have any reuse. There is pooling layers have low reuse. Right? Of course, like here I've shown with the stride of 2. So here you don't see any reuse. Here, actually, you just read once, you put the output. But for a different stride value, you could see actually some reuse. For example, suppose the stride was 1. Suppose stride was 1. Then you first read this, then you read this. Let me just give it. Suppose you first read this part, then you next read this part. So now this 4211, that is again reused. Okay, so that's why there could be some reuse. But if the stride is 2, there is no reuse here. And FC layers have no reuse unless you use batching. So I will explain batching little probably later. This presentation does not have batching, but later I will explain batching. So once you use batching, then FC layers also have reuse, but otherwise FC layers have no reuse, because as you can see, each input neuron is connected to each output neuron. So weights are not getting reused at all. Okay. So that's why FC layers don't have any reuse. Now FC and pooling layers, yeah, yes,
Batching
please.
is like grouping.
I will explain batching later. So actually, in batching, what we do, we supply multiple input images. Suppose you want to do image classification. Okay, suppose you want to do image classification, then you will supply not just one image. Suppose you will supply one image of dog, but you can also supply cat, cow, or car or airplane. So you can supply maybe 10 images simultaneously. Okay, and then because for every image, anyway, all the layers have to be applied. So you can, instead of applying your first layer on only one image, you can apply that first layer on many images simultaneously. You will get 10 answers. If you supply 10 input images, you will get 10 different answers at the end. So that is called batching.
Okay.
So, yeah, any other question, please? Okay. Now, FC and pooling layers have no data reuse. Actually, pooling layers can sometimes have data reuse. In general, they don't have data reuse. So that's why they require large bandwidth. So, see, as I already shown that, see, for FC layers, we'll have to read all the weights. And for pooling layers, we'll have to read all the input. And there is no reuse. That's why they need high bandwidth. So required bandwidth per layer on executing AlexNet on a device, which can have 100 giga operations per second with 100% efficiency. So here you can see that because convolution layers are compute intensive, they don't need much amount of bandwidth. You don't have to fetch a lot of data from memory. You can do a lot of computation. For each data you bring, you can do a lot of computations. So convolution layers have low bandwidth requirements, but pooling layers have high bandwidth requirement because they don't have data reuse. So this will repeatedly discuss this point, what is data reuse, because in architecture data reuse is important. Okay. So bandwidth requirement is high. Whenever there is no data reuse, bandwidth requirements become high. Okay. So is it clear till this point? So till this point we have discussed what are the characteristics of different layers of a scene. Okay. Now we'll discuss what are the characteristics of inference and training phases. So first of all, here is an introduction of what training and what inference is. Some of you may know about it. So what do we do in training? We take large number of input images. Suppose they are labeled, right? Now we try to train a neural network. We do many forward and backward passes. Okay, to teach the neural network what it is. So for example, here it is human. So over many forward and backward iterations, we try to see in forward propagation we try to predict. Okay, I say it is dog, but the computer teaches or our labels say no, this is not dog, it is human. You learn it is human. You learn it is human. You learn it is human. So slowly, when your network learns, just like we teach a child, right? Suppose like a child maybe 3 to 4 years. That time he or she starts learning many things. Of course, 7, 8. At each age, you can very clearly, distinctly see now the child has learned this much. He or she has started identifying it. Okay, so you can see maybe his brain or her brain is becoming very more evolved. So at the end of training, now our model is trained. What it means is the weights have reached proper value. Okay, the weights have reached the correct value. We have taught it. It predicted something. We corrected it. So with that we have finally come to the conclusion. Now during the inference we take any sample image. Right? Usually the number of images we take in inference is at a time is very small. For example, like you can install your any neural network based some algorithm in your mobile phone. Then you pass it some image, ask it to do some classification. Here we only do forward propagation. So inference means we only do forward propagation. So we supply any input to it, and then it will make a prediction whether it is human face or whatever. So smaller n right? And here, if you take more images, that's called batching. Okay, so this is the training phase. This is the inference phase. This is a very brief description. So during the inference, we actually use it. That's also called serving. Inference is also called serving, model serving. Okay, so and trainings usually happen once in a while. For example, like suppose Facebook uses certain speech detection algorithms or face detection algorithms. So let us talk about speech. So I speak, probably somebody from some other country, Spain. All of us may be speaking English only, but our accents are very, very different. So there could be one generic model, and then they will be customizing it for different countries. And usually, our speech doesn't change so frequently. So once you train a network, at least for next 6 months, you can use it. Then probably more words may be introduced, right? So then you may have to further train the system. So that's why training happens once in a while, and training can happen in the cloud. By cloud, I mean that this is a data centers. Every user does not need to do training because training is highly computation intensive. So we can get the trained model. For example, Alexa, right? I'm not advertising for it, but some that probably people have started using it. So now we are speaking English. Somebody else from a different country, they may be also speaking English, but our tone, our accent may be quite different. But hopefully they have trained it to understand the English of Indians, right? So with that, we can give some commands. Now, what happens? Actually, Alexa does not itself run the model. It records our speech. It sends it to the cloud, that means their data center. Now, in the cloud, inference happens. Okay, the models are there in the cloud. I mean, here inference also happens in the cloud, and then it sends the answer. Then it sends the reply to us. Right, and if your mobile phone is more powerful, you can directly, the computation can happen in the mobile itself. That means the inference is happening in the mobile phone itself. So that is the inference part. Okay, so I hope, is it clear what is the overall difference? So now there will be a lot of mathematical details to it. How do we do training? That is outside our purview. But I have explained what is the utility of training phase and what is the utility of the inference phase. Okay, so now let us see their architecture. So one more thing I will show. I don't have that slide. So yeah, actually one more thing which is that although training is highly computation intensive, but training happens once in a while, and inference happens very, very frequently. For example, in the NVIDIA and Amazon data centers, they found out that 90% of the computation demand is for inference. Although inference is very cheap, but just because it happens so frequently, that's why 90% of the computations happen for inference. Only 10% happens for training. Okay. So now let us see ease of parallelization. So in the inference, each inference is independent. So you can easily parallelize the inference servers. Parallelization of inference servers is very easy. However, training involves iterating over millions of examples. For example, here you can see this is a very large, and you will have to coordinate over all the examples and coordinating over parallel resources. And finally, by doing inference, by doing this forward and backward passes on all those images, finally you get a consistent set of weights. So parallelization of training is much harder. Okay, later in this course we will discuss one example of distributed training, where because training demands are so high, so we do training on suppose 10 servers or 1,000 servers. So after each iteration of backward and forward propagation, they will have to synchronize their weights. That's why parallelization is very hard. So if you have studied about Amdahl's law, you will know that whenever you have synchronization bottlenecks, parallelization becomes hard. Any questions? Okay, so parallelization of training is harder. Now, what are the compute and memory demands? So during the training phase, the backward propagation phase, we need to compute derivatives for every computation. How do we do it? That's mathematical part outside this course, but what we do, that's what we're discussing. It includes higher precision activation functions, some of which are transcendental. and we have to do multiplication by transposed weight matrices. So that's why compute requirements of trainings are much higher. For example, like your mobile phone, it can never do, I mean, usually it cannot do training, but it can easily do inference. And as far as the memory demands are concerned, during the training, we are updating the weights because we have some initial estimate of the weights, which could be wrong, which could be just initial guesses. So we update the weights, we try to reach the correct weights. So weight updates access intermediate values from forward and backward propagation. So we need intermediate values from both backward and forward propagation. So temporary storage can be 10 times the weight storage. That's why in the training phase, we need a lot of amount of temporary memory also, because we need to have a lot of temporary storage. Whereas in inference, weights don't change. This is another important property. So if you're designing, suppose an accelerator just for inference, you know that the weights are not going to change. This can help you to optimize your accelerator design. However, weights do change during the training. Okay. So for example, like suppose you may be designing a memory stuff, a ReRAM based accelerator. So because there are some EC students who are working on this problem, so that's why I'm explaining. So if you're doing training on ReRAM, so because during the training weights change, so every time you will have to update the weight which is stored in the ReRAM. And because ReRAM has limited endurance, you will see that the endurance fades. But it's very easy to design a inference accelerator using ReRAM, because weights are not going to change, so you don't need to do a lot of writes on the ReRAM. Weights are fixed. Okay, what is the precision requirement? So training requires high precision. Inference can even work with short integers like 8-bit integers or maybe like 16-bit floating point, half precision. But training definitely needs floating point arithmetic to fully capture the sum of many small weight updates during training. So that means we will be updating the weights by small amount. If you just use integers, all of those values will become 0. So you need floating point arithmetic so that those values do not become 0. Okay. Now, programmability. So training algorithms and models are continuously changing. So if your accelerator is such that your current model, it is the best, but it cannot be changed, then it will become obsolete. Because after 6 months, some new training algorithm will come, or some new models have to be trained. For example, for speech, previously people were using LSTM. Nowadays they are using BERT. So if you just design an accelerator which can just work for one set of algorithms and it cannot be changed, then it will very quickly become old. Why? Because newer models are coming every day. Okay, so these are the so from this at least you can understand that training is hard, inference is easy. Okay, but because inference happens so often, inference is also important. But it is much easier to design an accelerator for inference than for training.